Hello everyone, welcome to the lecture video on vapor and combined power cycle chapter. Today we're going to talk about the cogeneration. In the previous lecture we talked about the regeneration, right? We saw that how we can take the turbine outlet and then you know regenerate the steam using the turbine outlet from the pump. So we used two different type of heating system as well, closed feed water and open feed water heater, right? So today's topic is cogeneration. Cogeneration is nothing but this topic is simply telling us that two type of generation is happening at the same time, right? So one type of generation, or the type 1 would be the electricity production, and type 2 is that process heating, right? So basically the definition of the cogeneration is the production more than one useful form of energy. So it could be type 1 process heating, and then type 2 would be electricity, right? So from the same amount of energy. So cogeneration is the production of more than one useful form of energy from the same energy source. How? Let's take a look on this diagram. So basically when we take the Rankine cycle, we saw that instead of here in this unit 4 to 1 we use a condenser, right? So that condenser is basically rejecting the heat to the environment. All the heat is kind of considered as a waste heat, right? However, if we replace that heat, or somehow if we can utilize that heat, right, to heat up the water, or utilize that heat for some sort of work, or to generate process heating, then we can increase the cycle efficiency, as well as we can reduce the cost of the operating cost of the cycle, right? Overall operating cost of the cycle. So how can we do that? So basically in industrial process heater, so we can use those process heater to take that heat and utilize that heat, maybe for heating the water, or to generate electricity or whatever. We can utilize that heat, utilizing that by utilizing the process heater instead of a compressor. And then process heater is also acting as a condenser. How? This process heater is also rejecting that heat. However, that heat is in useful form, right? We can use that heat and then condense that liquid. So now how we can utilize all form of energy? Let's take a look. So in the boiler we are putting 120 kilowatt of work, right, Q in the boiler. So in the process heat, or in the cogeneration system, ideally the two form of energy is produced, or energy is being converted. Type 1, the energy is the process heat, and type 2 is the electricity. So if we look at this turbine, this turbine is producing this 20 kilowatt out of 120 kilowatt, and then rest of the heat is basically rejecting, right, which is 100 kilowatt. Now if we can somehow use this large amount of energy, 100 kilowatt, as a process heating, then basically we can see that we are getting two output. Number one is that this turbine output, and number two is this process heating output. So that's the definition of the cogeneration. In actual power plant, or real application, they use modified cogeneration system. So let's take a look how is that, right? How the modification look like. So this is a modified cogeneration system, right? Cogeneration power plant. So basically, if we look at this diagram, then we'll see. Let's start from the pump, right? So if we start from the pump, then we can see that the pump, the task of pump or necessity of pump is to pressurize the increase the pressure head of the liquid. So basically that is delivering that liquid to the mixing chamber. Mixing chamber is nothing but mixing of the vapor and liquid, right? And the liquid vapor mixture is coming to the boiler, and from that boiler, once it's getting superheated, now you can see we expressed this one as the number 1. So that number 1 would be the maximum temperature, right? Number 1, number 2, and number 3, they will be in maximum temperature, right? So in the boiler 1, when it's exiting from the boiler, some part of that vapor we are taking to the process heater, and some part of the vapor we are taking to the turbine. So now in the turbine we have two outlet. One is coming to the process heater, another it's completely expanding and coming through the condenser. Again, from the process heater, basically we are taking heat out, q out, right? Q out of process heating, excuse me, q process heating. Basically we are taking out some or rejecting some heat in useful form, right? And also the condenser is also rejecting the heat, right? Q out. And it's continuing the cycle. So basic modification is that right here, right, in the boiler exit, right? So in the boiler exit we are taking two outlet. One is to turbine, one is to process heating. So if we look at the TS diagram, then start from the 1, then we'll see 1 2 3, all of them are the same point. However, from 2 to 4, it's expansion valve. Basically expansion valve means reducing the temperature a little bit, right? Reducing the temperature here, expansion valve. And then also expansion valve means reducing the pressure, right? So it's reducing the pressure right here. So and then from 2 to 5, it's a turbine exhaust 3 to 5. However, that 5 point is not completely expanding, right? So 5 is coming here. However, the complete expansion is happening at 0.6. So this is the 0.6, and then we will see that the 5 and 6, two different pressure so line. So this is one pressure line and this is another pressure line, okay? And then again it's the same thing. 6 to 8 is the condenser and 5 to 7 is the process heating. So once we do that, then again we are using two different pump which is 8 to 9 and 7 to 10. So we see that 8 to 9 is pressure is increasing and 7 to 10 is pressure is increasing. And then from 9 to 11 mixing chamber, 9 to 11 we can see this is the mixing is happening right here, okay? And then from the 11 to 1, basically this complete heating process, right? Constant pressure heat addition is happening right here. So if we do the analysis of this this modified cogeneration plant, then we'll see where is heat addition is happening, where the heat rejection is happening. Let's take a look. So before that, I would like to define one definition which is called the utilization factor, right? So utilization factor, what is that utilization factor? What is that utilization factor? So utilization factor is nothing but it's defining that how much heat in is happening right here in the boiler, and how much heat is how much energy is producing in turbine, and how much energy is producing in the process heater. So basically output versus input, right? So it's kind of efficiency, but rather in efficiency we're trying to define this utilization factor in terms of like one single output one single input versus two output, okay? So basically the utilization factor equals to net power output plus process heat, right? So how much process heat is delivered divided by total heat input, right? So basically net power output equals to W net plus process heating, we express QP divided by the Q in, right? So that's the definition of the utilization factor, or we can simplify the utilization factor equals to 1 minus Q out divided by Q, excuse me, Q in. It's the same, right? So this is the definition of the utilization factor, or we can use this one as a definition for utilization factor. So now let's take a look at this enthalpy, right, at each individual point enthalpy, and then we can determine that what is the Q in, what is the Q out, and what is the process heating, right? So the first thing is that Q in equals to mass times, you can see that what is the Q in is happening right here, right? So this is the Q in, or the boiler, right? So the Q in is happening H4 minus H3, excuse me, this one. So for this diagram we can see that Q in is happening, so this is our boiler, so it would be H1 minus H11. So H1 minus H11. So this is our Q in, right? And then Q out, mass times Q out in the condenser, which is right here, H6 minus H8. H6 minus H8, right? And then we have the process heating, Q process heating, excuse me. And where is the process heating is happening? Process heating is right here. This is the process heater, right? So the process heater, two different type of the heating is happening. One is that, so if we consider this one as a how do I say, this is M2, this is M3, right, mass flow, and this is M1, right? So then what is happening, and then M3 is basically dividing like M5 and M6, okay? So here it will be M2 times H7 minus H4 plus M5 times H5 minus H7, okay? So the process heating, excuse me, this Q in would be M1, Q out would be, which one, excuse me, this is M6, okay? And then Q process heating, basically here M2 times H7 minus H4, and then M5 times H7 minus H5, okay? M2 times H7 minus H4 plus M5 times H7 minus H5. Excuse me. Okay, so this is the process setting, and then turbine output, W turbine, which is equals to, we can see that how much would be the turbine output. So basically the turbine output is nothing but the M4 minus M5 minus M6 right here. So basically it would be, if we take a look, the turbine would be, if turbine inlet is equals to M3, instead of M5 and M6 we can write it in M3. So M3 times we can see that there will be two output, turbine output, 3 to 5 and 3 to 6. Instead of M3, let's write this one. So it would be M3 minus M6, which is equals to M5, right? M3, excuse me, m3 minus m6 equals to h3 minus h5 plus m3 minus m5 times h3 minus h6. Okay, so this is the turbine output. So basically these are the expression. We just need to take a look at this, define that mass flow of each of the inlet and outlet, and subtract that, the enthalpy, or subtract the enthalpy from the output to the input. So then we can calculate the what is the q in and what is the q out. So that's all about the cogeneration plant, right? Now let's move on to the last topic, which is the topic combined power cycle, right? So basically 10.9 is that combined gas vapor power cycle. So this topic is itself is telling us that what we are going to do, right? So combined gas and vapor power cycle. So in chapter 9 we talked about the gas power cycle, and chapter 10 this is basically the vapor power cycle, right? Brayton versus the Rankine. So in this topic we'll combine them. How can we combine them, right? So let me export a picture of these two, which is basically representing the excuse me, this one. I don't need this one. Okay, so this is the picture. I took it from the textbook, right? The combined excuse me combined gas power vapor and gas power cycle. How? So let's take a look at the Brayton cycle. What we had in the Brayton cycle, we had a compressor, we had a combustion chamber, and the turbine. And then turbine exhaust is basically exhausting in the open environment, right? However, instead of in open environment exhausting that open environment, if we use a heat exchanger, okay, then we can utilize that heat. How? In the Rankine cycle, what we have a boiler, right? So and that boiler is basically the task of that boiler is basically converting the liquid into the gas or the vapor, right? So now instead of the replacing the boiler, we are using the heat exchanger. When the pump is delivering the liquid to that heat exchanger, it's coming out as a vapor, right? It's already in the vapor. So that's how we basically combine these two cycle. This is the gas power cycle, which is the Brayton cycle, right? And this is the Rankine cycle. So we can combine them just by utilizing a heat exchanger and replacing the boiler, right? So that's the combined vapor power cycle, and people uses this combined gas and vapor power cycle in the power plant. And also the efficiency of this power plant is very high compared to the individual Brayton cycle or gas power cycle, or the vapor power cycle. And then this is the corresponding diagram of the TS diagram. Okay, one point I would like to mention right here is that why the efficiency is higher in this process, because imagine that you have a Brayton cycle operated power plant. You are basically rejecting all the heat to the environment, so you are losing a lot of heat right here, right? Imagine that you have a vapor power cycle. You are utilizing a boiler, and to heat that boiler, or to raise the temperature in the boiler, you are using lot of, like, you have to put lot of Q in, right? Either it could be nuclear energy, to coal fired energy, right? So instead of you use those energy or the Q in, you are simply utilizing a heat exchanger, which is basically reducing the cost and increasing the efficiency, right? So in this combined power plant system, the TS diagram will look like this. It will have two different diagrams. So right here you can see that this is the gas cycle, which is nothing but the Brayton cycle, and here you can see the steam cycle, right, which is the mixture of the vapor and liquid. So that's why this cycle is mostly belongs to the this saturated dome. However, the gas cycle is mostly outside of this saturated dome. Now now let's ask the question, where is the heat addition is happening, right? So the heat addition is happening between process, let me clear it a little bit. Okay, so the question is that where is the heat addition is happening, right? So if we look at this diagram, basically here is the heat addition is happening, right? The combustion chamber, right? So only one combustion chamber heat addition is happening, which is 6 to 7. Let's consider the gas cycle first. So that we see that in gas cycle compressor, from 5 to 6, its pressure is increasing and temperature is increasing, and then 6 to 7, it's a constant pressure heat addition, right? Excuse me. And then from 7 to 8, it's expansion, and then from 8 to 9, right, basically the heat rejection, right? And that heat is basically accepted right here by this other cycle, which is process 2 to 3. So if we look at this process 2 to 3, this is also constant pressure heat addition, constant pressure heat addition, right, in this cycle. And then from 3 to 4, we can see that basically it's expanding through the turbine, W turbine, and then 4 to 1 condenser, which is Q out right here. And then from condenser to the pump, excuse me, so from the pump to 1 to 2, it's basically again increasing the pressure and temperature slightly, the temperature of the saturated liquid, right? So that's the combined vapor power cycle, right? So combined vapor and gas power cycle. So I mean, if we do a math problem, then we'll see, we'll gonna go ahead and solve a math problem based on this gas and vapor power cycle, and then we'll see that how to determine the Q in, how to determine the Q out, right? And we also will see that the efficiency is, it's becoming really high compared to the individual cycle, for example the Brayton cycle and the vapor cycle. So the efficiency of the thermal efficiency of the combined, it's greater than the gas power cycle, right? Gas power cycle, which is also greater than the thermal thermal efficiency of the steam or vapor power cycle. Okay, so we'll take a look of this statement by solving a math problem. So thanks for watching this video. That's all about today's class. We'll go ahead and solve a math problem.